All right. Hello, everyone. Thanks so much for having me, and thanks so much for joining this seminar. I'm Shuyuan Yu. I'm currently a postdoc, as Sean just introduced, at Carleton University, working with Dr. Jan Lafayette, Dr. Rebecca Muckley, and Dr. Heather Douglas. And today I'd like to share my work with you on cognitive supports for analogical reasoning in rational number understanding. And these work were done during my PhD at the Ohio State University, working with Dr. John Opfer. A central question in developmental psychology, the so-called Plato's question, is how do I learn so much from so little? Well, the audience in this group probably are pretty fast to think that analogy might provide an answer to this question, because analogy can bootstrap learning from only limited input based on the structural similarity. It is a pretty powerful mechanism of cognitive development, and it is widely used in science and everyday life. For example, when William Harvey compared a heart to a water pump, a productive scientific model of blood circulation is created. A heart is like a water pump because in both systems, a change of pressure leads to an increase of the flow. Through this analogy, people feel an intuitive grasp of how the heart works and also develop a new, more abstract understanding of the meaning of the pump. This more abstract, more general form of knowledge representation is a schema. Schema is an organized system of relations. By having a schematic representation of what a pump is, when we encounter new exemplars of pumps in the future that look nothing like what we have ever seen before, we can use our pre-existing knowledge structure of pumps to imply how these kind of pumps work in these novel situations. So schema abstraction is helpful for analogical transfer. Yet schema abstraction also often requires cognitive support. According to the structure mapping theory, comparison facilitates schema abstraction by facilitating comparison between the source and the target, helps to highlight the one-to-one correspondence of the elements between the two structures, and then facilitate the abstraction of the common relational structures and analogical transfer in the novel situation. This kind of analogy making process allows us to extrapolate what is learned far beyond the training space. And indeed, experimental evidence support that comparison facilitates schema abstraction. For example, when college students read two cases of a negotiation situation that shares the same strategy, but in two different knowledge domains, and after that, they were tested whether they can transfer the strategy to a third novel situation. And during learning, some students read two cases on one page and were asked to compare the similarities between the two cases. And other students read the same two cases one by one, case one, and then page two, case two. Results show that comparison leads to better quality of schema generation compared to separate group. And also, these schema quality predicts analogical transfer. That is, whether the participants would use the same strategy in the novel situation, case three. And here I propose that number line can serve as a mathematical schema on the number system, because the number line represents the relation of numbers. For example, when children count a set of dots, there's a lot of relation over here, the relation of an increase or decrease in the temporal order of finger pointing objects, and an increase or decrease in the count list, 1, 2, 3, 4, 5, an increase or decrease in the quantities they represent, or the serial order of integers. And these relations can all be conceptually mapped onto one another and to the mental number line, highlighting the common relation that 5 fingers is the next of 4 fingers in counting. The number word 5 is the next of 4. 5 dots is the next of 4 dots. And these kind of mapped representations takes time to form. Young children only have pretty vague representations and only relate a little with really small numbers and a lot with large numbers. And it takes development and education for children to form an extending linear structure of the number line. So now the question is, how can this number system support numerical understanding and reasoning? Well, previous studies indicated that alignment between small and large integers on number lines helps young children better understand large numbers that they rarely encountered. So by making the analogy that 15 is to 100 as 1,500 is to 10,000, second graders gain a better understanding of the decimal system and thus have a more accurate estimation of large number that they rarely encountered. And what about fractions? Can we apply the same methods? Fractions are pretty important concepts to learn because they are the gateway to algebra, which is the gateway to both educational and professional success. Despite their importance, fractions are also notoriously difficult to learn. Both children and even highly educated adults have considerable challenges with fractions. And one confusion with fractions is from this cross-matching between integers and fractions. When you look at the values of the numerators, the value of fractions increases linearly as the value of the numerators increase, just like integers do. However, when you look at the values of the denominators, then the value of fractions decreases as a power function. And this is not only confusing for children, but also causes adults problems as well. Therefore, early research on fraction learning proposed that our innate number sense evolved to handle these discrete quantities, thereby rendering the concept of fractional number pretty counterintuitive, suggesting that integer understanding was qualitatively different from and even interfered with fraction understanding. Then how to build fraction knowledge on our pre-existing integer knowledge? The overarching aim of this talk is to apply the learning mechanisms of analogy to math education. Study 1 and 2 exams how well children's number line representations are and whether or not a comparison between integers and fractions on number lines can facilitate number line representation. Study 3 further look at the transfer effect and the effect of different analogical sources on transfer. Finally, study 4 and 5 investigate whether or not the quality of the number line representation would facilitate explicit proportional analogy. So first of all, study 1, let me take a step back and talk a little bit about how well children estimate to integers and fractions on number lines over development. 3rd to 5th graders estimated fractions and integers on number lines that were proportionally identical to the upper bound of the number line, like 3a is to 1 as 3 is to 8. There are different kinds of number line estimation tasks. In the number to precision task, children will mark a given number where the given number is on the number line. And in the precision to number task, children see a mark on the number line and will produce a number that is corresponding to the position. Besides number line estimation, children also compared to fractions and ordered 3 fractions from the smallest to the largest. So how is the development of number line estimation? Here I plotted percent absolute error as a function of grade. Percent absolute error just captures how deviated children's estimation is to the true value on the number line. Basically, the lower PHE is, the more accurate children's representation is. So here I present integer PAE in red and fraction PAE in blue. The lower means more accurate. And as shown in the figure, there were few errors for integers and fractions, not very surprisingly, and also discrete errors decreases as grade increased. And more importantly, there's an interaction between grade and format. In other words, the advantage of integer format over fractional format reduced as grade increased, suggesting a more coherent representation of integers and fractions with education. Now we want to further quantitatively measure this representation coherence and investigate whether or not a more coherent representation between integers and fractions will predict better fraction proficiency that is measured outside of number line estimation test. So to answer this question, we calculated a measure called the representation coherence, which is the correlation between estimates of proportional equivalent integers and fractions. And we observed that the representational coherence independently predicts fraction proficiency beyond the grade for both comparison task and the ordering task. The more coherent children's representations are, the more accurate they are in comparison and ordering and in general fraction proficiency. So basically, study one, we examined the developmental trajectory of integer and fraction estimates. And we know that through development, children's representation of integers and fractions are becoming more coherent. And we observe that this representational coherence independently predicts fraction proficiency, which may imply that it's important to build a coherent representations of numbers. Well, study one sets some groundwork, and it has little to do with analogy, as you might have been wondering so far. But this data pattern is consistent with our hypothesis that analogy generally serves as a learning mechanism that helps children extend their mental number line from familiar numbers to novel numbers. And if this is right, then setting up an experimental intervention that facilitates analogy would be expected to lead to changes that normally seen in development, as we observed in study one. So in study two, and the following studies, we designed a series of educational intervention to examine this. First, we want to investigate whether or not comparing the values of fractions and integers on number lines improve understandings of fractions. So in study two, we examined whether spatial alignment facilitate fraction learning by analogy. By presenting children integer and fraction number lines spatially aligned, we hypothesize that alignment between integer and fraction number lines can reduce the two-part relation to a single position that has a real magnitude, so children can use their pre-existing integer knowledge to bootstrap an understanding of fractions. And to investigate this, we tested an educational intervention using a pre-test training post-test design. We randomly assigned 3rd to 5th graders to one of the two training conditions, alignment and no alignment. At pre and post-test, children needed to estimate the position of fractions on a number line. During training, children in the alignment group were given 4 couples of number lines. They are vertically aligned for each trained magnitude. Thus, they have a chance to compare the integer and fraction problems and make proportional analogies that, for example, 3:8 and 3:8:1. And in the no alignment group, in contrast, children completed 8 lonely number lines. Items were the same as alignment group, but they were presented sequentially and in a randomized order, thereby blocking the ability to compare the problems. In neither condition were children instructed to compare the problems, nor did they receive any feedback on their answers. Also, we tested a group of college students to establish a criterion we would like children to achieve ultimately. So what did we find? Here I present during the training session, children's errors with fraction estimates on number line test. So again, a lower bar here means more accurate. Here is the errors for children in the no alignment group in blue, of course, fraction number line task and integer number line task. And here is adults' performance denoted by the dashed line. Not very surprisingly, adults are much more accurate with fraction estimates than children. And now the question is, are children in the alignment group doing better than the no alignment group, and are they almost as well as adults? And what we found is that, Yes, children in the alignment group were significantly more accurate with their fraction estimates than the no-alignment group, and they were as accurate as adults across fraction number line tasks, number to position tasks, and position to number tasks. So alignment worked. But can the training effects transfer to post-test when these integer number lines are not available anymore? So we did parallel analysis for the post-test. And what we found is that we found the same result pattern as training. Here we presented children's errors during post-test, of course, for these 4 different kinds of number line estimation tasks. And we saw the same result pattern that children in the alignment group made fewer errors than those in the no alignment group, and they were almost as well as adults. So we found that training effects persisted at post-test. The study 2, to sum up, shows that a very short one-session training of alignment between integers and fractions on number lines leads to children's better understandings of fractions, suggesting that comparison facilitates abstracting the schema that fraction are also numbers that denote magnitudes and can be placed on number lines. But the limitation of study 2 is that we did not control for accepted functions, children's standardized math achievements, and also there are more questions to be answered. For example, how broad and durable is this training effect? And also, what about other analogical sources, such as percent, which might also provide equally powerful analogy? But before I go into the study 3, are there any questions so far? All right, so let me move on to study 3. Here I need to change back and forth to look at chat and the screens. All right, so let's move on to study 3. So to answer the question about whether alignment leads to broad and durable gains, study 3 tested another 3 different analogical sources: integer prepared, percent prepared, and fraction prepared. The integer prepared group is the same as what I just presented in study 2. We present children fraction number lines vertically aligned with integer number lines. And we want to check whether other analogical sources helped. So we also designed a parallel condition called the percent prepared condition, where everything is the same as the integer prepared condition, but we replaced all the analogical sources of integers with percent. So here the analogy is 38% is to 100% as 3/8 is to 1. And in the fraction prepared group, everything is the same as the integer prepared again, but all these integer analogical sources were replaced by fraction number lines. Basically, children practice twice this fraction knowledge. And finally, in the control group, it's pretty much similar as we just presented in study 2. Children did all these same questions, but the top question disappeared after completed, thereby blocking this opportunity for children to make the comparison. To investigate the training effect, whether that transferred to a broad and durable gains in fraction proficiency, study 3 also enlarged these testing batteries. Besides the number line training task, we also include other tasks beyond number line estimation. So for the number line task, it's the same as we just presented, but they extended to larger numerical ranges, 0 to 1, 0 to 2, and 0 to 4. And also we present novel magnitudes for children to estimate that were not trained before. Beyond number line estimation task, children also compare 2 fractions, order 3 fractions from the smallest to the largest, categorize a fraction into one of the 5 boxes, almost nothing, some, half, most, almost everything, and the sum fraction arithmetic. Besides fraction proficiency test battery, we also measured children's executive functions. We measured children's working memory updating by letting children remember the last 3 letters of a letter list, and also measured children's inhibitory control by asking children to do a flanker task. Finally, we collected children's standardized mathematics achievement score as a covariate to control for as well. To examine whether this training effect lasted over a delay, after about an average of 15 days after training, children completed the post-test that contains the same testing battery as pre-test. We also included a group of college students that completed the same testing battery to see how well children will ultimately, these 4th to 5th graders will ultimately achieve, how much room we can help children to improve. So this is the basic study procedure. And our first question is, do these different analogical sources help in training? Here I present during the training session, children's errors with fraction estimates. The lower the bar is, the means more accurate. Here's the error for children in the control group in gray across 2 different fraction anomaly estimation tests. And not very surprisingly, we replicated our previous study that alignments to integers worked, right? Children in the integer prepared group have fewer errors than children in the control group and were better than adults. Then how about percent and fraction prepared group, these middle 2 columns? And what we found is that, yes, different analogical sources of percent and fraction also helps to facilitate a better representations of the fractions, as long as these analogical sources are presented in front of them. And that alignment to analogical sources of integer, percent, and fraction all worked. Then can the training effect transfer to post-test after a delay? And can the training effect transfer to a more broad fraction testing battery? To answer this second question, does training leads to broad and durable gains? We calculate a total score of each child at the pre and post-test fraction testing battery. And here I'll present the accuracy that is adjusted by children's grade, standardized mathematical achievement, executive functions, and pre-test fraction accuracy, so that we can see the effect of training controlling for all the covariates. So here I'm presenting children's accuracy in the control group. So this time, this is accuracy. So the higher the bar is, the more accurate children's fraction proficiencies are. And children in the control group at the post-test were significantly lower than adults. And what we found is that alignments to percent and fractions conditions were also significantly lower than adults and did not significantly differ from children in the control group, suggesting that alignments to percent or fraction prepared did not transfer to the post-test battery after a delay. Then how about the integer prepared group? Does training leads to broad and durable gains? And what we found is that compared to the control group, the odds of the child in the integer prepared group correctly solving an item in the fraction proficiency test battery actually increased by 40%. It is not significantly different from adults' performance as well. So we found that only alignments to integers persists after a delay when these analogical resources are not there available anymore. And only alignment to integers transfers to other fraction tasks. The study three, to sum up, shows that alignments to integers leads to broad and durable gains in fraction proficiency, and it highlights the importance of building new mathematical knowledge through analogies to these highly familiar sources. So then our next question is, can magnitude knowledge in turn facilitate more explicit proportional analogy. All right, so before I go to study 4, are there any questions so far? All right, so I'll move on to the next study. So in the study 4, I will again take a step back and talk a little bit about the development of analogical reasoning. There are 3 accounts to explain why children develop different kinds of analogical reasoning skills. And one account is the executive functions account, which emphasizes the role of domain general executive functions in analogical reasoning. And more specifically, it says that young children's limited working memory capacity and their lack of inhibitory control leads to the failure of processing complicated relations. Instead, children tend to focus more on the superficial perceptual similarities. And in contrast to the view that analogy arises from high-level domain general cognitive abilities, the relational priming account states that analogy requires the ability of pattern completion that is independent of the context. Analogy does not lie in structured representation and structured mapping between bases and targets. Rather, it arises from substantially different low-level cognitive mechanisms. And finally, the knowledge acquisition account emphasizes the role of domain-specific knowledge in relational reasoning. In support of this view, correlational evidence suggests that young children who have better knowledge of proportions can better solve these proportional analogy questions like this. Half a circle is to half a rectangle, as a quarter of a circle is to what? I'll give you a few seconds to think about this question. Choose one from below to finish the pattern. And the correct answer here is here, a quarter of a rectangle. However, in this kind of multiple choices questions, choosing among the relational match, D here, and between these perceptual matching these structures here requires cognitive resources of inhibitory control. Children might just not be able to inhibit this tendency to choose choices that look so similar to the terms presented. Therefore, whether or not the domain-specific knowledge itself facilitates analogical reasoning is unclear. So that's the aim of study 4. We want to focus on examining the knowledge acquisition account by investigating the development of the ability of a super simple 4-term analogy questions like this. Participants saw 2 aligned number lines like this, where depicting the position of 3 on 0 to 8 number line, the position of 3 A's on 0 to 1 number line, and they're asked to fill in the blank. 3 is to A's, as 3 A's is to what? But to succeed in this task, all participants need to do is to fill in this missing component from the aligned structure that are readily available in front of them and complete the pattern. By providing these relational structures readily available, we aim to control for and minimize the effect of executive functions. So to explore whether domain-specific knowledge matters, in study 4, we asked participants with different educational backgrounds to complete a 4-term analogy production task across different types of domain knowledge. They are asked college students, court-sourced adults, 3rd to 5th graders to complete a letter task, a magnitude task, an integer task, and a fraction task. All these 4 tasks are designed similar. They all have this analogical structure right in front of them. The only thing that differs are the knowledge required, whether those are letter lines, whether those are magnitudes, which are the length of the length of A to length of B is the same as length of C to length of D, and the integer number line 3 to 8 as 300 is to what, and for the fraction number line I just presented. And we want to see whether this domain knowledge of fractions really matter in this kind of very simple tasks. Of course, children and adults from different educational backgrounds. So here I present the accuracy of the analogy task across these different domains: letter, magnitude, integer, and fraction, and participant groups. And we found that accuracy of fraction for term analogy questions yielded is the lowest among these 4 different tasks. So that's very interesting because all the relational structures are readily available to them. But still, we found that even with exact alignment between these analogical targets and sources, accuracy on fraction analogy was still lower than accuracy on other problem types, indicating that prior knowledge of fraction magnitude may be critical to solve these proportional analogy questions. However, in this study, we did not explicitly measure participants' knowledge of fractions. So to further validate this causal link that more domain-specific knowledge leads to better analogical reasoning with proportions, Study 5 further used an educational intervention to examine this knowledge accretion account. The Study 5 used this pre-training post design to examine the knowledge accretion account and answer the question whether or not training on knowledge of fraction magnitude would improve proportional analogy. We randomly assigned 3rd to 5th graders to one of the 3 training conditions. At pre-test, children needed to estimate the position of fractions on the number line as a measure of their fraction estimation proficiency. And during training, their children were randomly assigned to a conceptual group, a procedural group, and a conceptual plus procedural knowledge group. The conceptual knowledge training group emphasized that the conceptual knowledge of fractions, which is fractions are a kind of number that measures quantity using real-life examples like Emil had one chocolate bar. The chocolate bar had 10 parts. Emil ate this much. What number of chocolate bars did Emil eat? And this number is between 0 and 1. When we need to measure something that is between 0 and 1, we have to use a special number called a fraction. And it's like that, and kids like to watch Emil. And the procedure knowledge training group served as an active control group, emphasizing the exact steps to estimate fractions on number lines. For example, here the question is where is 9/10 on a number line below from 0 to 1? And children were explicitly told the certain steps of doing this. To estimate the position of a fraction on a number line, follow 2 steps. First, you would multiply the right-hand number by the denominator. And then you would estimate the position of the numerator. Finally, the conceptual plus procedural group is the combination between the conceptual group and the procedural group to see if there is an additive effect. The sequence is always conceptual first and then procedural. And after training, children completed 4 terminology questions as what I just said in study 4. They see 2 number lines and were asked to fill in the blank where this alignment structure is readily available to them. So our first question is, does pre-test magnitude knowledge predict performance on proportional analogy? So here I'm presenting the accuracy of the 4-term analogy questions as a function of the pre-test number line estimation error. And we observed a negative correlation between the pre-test estimation errors and the accuracy analogy questions, indicating that children with poor magnitude knowledge of fractions failed to produce correct analogies. But it will also be that smart kids do everything well, right? So what we're really interested in is that does training improve performance on proportional analogy, even controlling for their accuracy at pretest? And then we next examined this effect of training conditions, and we found that the conceptual knowledge training yielded the highest accuracy among the conceptual knowledge training group, procedural group, and conceptual plus procedural training group, suggesting that the conceptual understanding of fractions facilitates proportional reasoning. However, we did not observe an additive effect of a combination of conceptual and procedural intervention. So to sum up, study 5 shows that conceptual understanding of fractions facilitates explicit proportional reasoning. It provides both correlational and experimental evidence that analogical reasoning is not simply just pattern completion or due to the maturation of exaptive functions, but depends on these domain-specific knowledge. It is consistent with the knowledge acquisition account. Making correct analogies among the terms actually requires an understanding of what the term stands for, even when these relational structures are aligned and readily available. And practically, these studies shed light on how to teach explicit proportional analogy on STEM education curriculums. In conclusion, this series of studies showed comparison leads to schema abstraction, and then good schema leads to more broad and durable gains. And finally, the schema quality affects explicit analogy. Number line serves as a schema to facilitate both the development of rational number understanding and also, in turn, explicit proportional analogy. And rather than integer being an obstacle to fraction learning, pre-existing integer knowledge can be a stepping stone when instruction draws on the power of good analogies. Finally, many thanks to Dr. John Upfer, my advisor at The Ohio State University, and my lab members at the Developmental Cognitive Science Lab. Thank you to Dr. Carson Thompson and lab members to the Cognitive Developmental Lab at the Kent State University, IES grant for funding these studies, HENDA and childrenhelpingscience.com for hosting our studies during the pandemic, and all the research assistants, families, schools, and teachers who participate in our studies. Thank you all so much for your time, and I'm ready to take questions.